Welcome to evaluating the definite integral. Right, so we're going to use some properties of our definite integral to evaluate area under the curve. Actually, all of these would be positive that we're going to look at, so it really would be area. All right, so let's look at the first one. We had a couple rules that we've learned for integrating. All right, so we're going to integrate the 2x. Right, so that would be a power rule. So we'd increase the exponent by 1, divide by the same thing. The 1 over x, that is not a power rule. Right, so if you have x to the negative 1 or anything to the negative 1 or 1 over anything, that is not going to be a power rule. This is going to be natural log of x. Normally we'd put absolute value bars because x, that's got to be positive. We're evaluating, so really those absolute value bars don't matter because we're plugging specific values in. So I'm not going to even bother to put absolute value bars in. And then this would be plus x. There's no, by the way, there is no c when we, so remember we had that constant that might get lost. This is not a function. Right, so we are evaluating, there's no c when we are finding the definite integral. So you do not have to worry about adding plus c because that's not part of the definite integral. We are only evaluating the function we have and then integrating with the function we have and then evaluating, and there's no added constant. That's only for when we're finding the family of functions. That's the antiderivative for that. Okay, so let's simplify that. And oh, by the way, we have to read this. So we are evaluating from 1 to 5. Make sure you write that in. Okay, so because this is our definite integral. Let's reduce here. That would be x squared minus natural log of x plus x evaluated from 5 to 1. Right, so that's going to be, now we're going to plug in. So we have 5 squared minus natural log of 5 plus 5. And then don't forget your parentheses because you're subtracting all of this. 1 squared minus natural log of 1 plus 1. Right, so 5 squared would be 25 minus natural log of 5 plus 5. And then this in the parentheses is going to be 1. Natural log of 1 is 0, right? Because e to what power is 1? Well, that'd be e to the 0. And then plus 1. All right, so this is just going to be 30 minus natural log of 5, and that's just going to be minus 2. So our final answer here, I should have wrote a little bit smaller, is going to be 28 minus natural log of 5. And you can leave it like that, the exact answer. Right? Don't worry about getting a decimal equivalent for it. I really would like to put this up in a line, but I guess that looks just fine where it is. Right, so there's our answer. Right, so put this one in your notes. We're going to look at some properties. Actually, we're going to look at one more integral, and then we're going to look at some properties. All right, here's our next one. So find the area enclosed by the x-axis, the vertical lines x equals 0 and x equals 2, and the graph of y equals 2x squared. All right, we know what the graph, 2x cubed. For some reason, it is not typed right and it does not match. We know what the graph of 2x cubed looks like, right? Everything from 0 to infinity on the x-axis is going to be above the x-axis, and everything from 0 to negative infinity is going to be below, right? So we know this is because we're evaluating for positive numbers. We know it's going to be above the x-axis, and it really does represent area under a curve. All right, so we'll just integrate. This one is the power rule. Right, so we have 2x, we'll increase that by 1 to the 4th power and divide by the same thing. And we're evaluating from 0 to 2. We'll reduce that. Oh, let me put a equals. So that would be x to the 4th divided by 2, and we're evaluating from 0 to 2. Right, I'm just going to put this over here. Right, so that would be 2 to the 4th divided by 2, and then minus 0. Right, that'd be minus, I'll just write it in, minus 0 to the 4th divided by 2, which is 0. So our answer is going to be 16 divided by 2, or 8. And we could actually do a limit of Riemann sums here with this one and find that area. We haven't done a cubed. Maybe I'll do one in class. Let's look at a few properties of our definite integral. All right, so we've gone over a couple of these. So if your starting and ending value are exactly the same, then when our numerical value for our integration is going to be 0, right? Because you basically have a rectangle with no width. If we have an integral, we want to switch the limits of integration. We want to switch our starting and ending value. You can do that. And it just changes your answer to the opposite. The integral of a sum or difference of functions is the same as the sum or difference of the integral. So you can split up a integral that's a sum or difference into separate integrals. And sometimes that's easier to evaluate that way. And then here is a property of integrals, where we can take two integrals and combine it and make it one integral. And just have a couple requirements. Number one, has to be the same function. Can't go combining different functions. And which function would you pick? You need one function here. So you have to have two integrals of the very same function, and one has to end where the other begins. So notice here that the first integral goes from a to b. The second integral goes from b to c. So where one ends, the other picks up. We could rewrite that as one integral and just make that from a to c. And that comes in handy when we know the areas and we want to be able to combine them, like in the next problem. All right, so you can add these ones. I think the first one's in your notes. I wrote a couple others. All right, so we want to integrate, and we want to find the answer for the integral of h of x dx from -2 to 5. Notice there is no -2 to 5 there. There's a -2 to 3. And there's also a 3 to 5. Okay, so write this in your notes. So notice one ends, or one picks up where the other ends, right? So the second one here picks up, it starts where the first one ends. So we could combine that into one integral, right? So those two integrals are the same thing as the integral of h of x dx from -2 to 5, right? Because one begins where the other ends. And so now we can evaluate, right? So from -2 to 3, that was 6. From 3 to 5, that was 7. And so our answer is 13. I would like you, when you're solving these, to write down the separate integrals that you'd be combining, and then you can write down their numerical answers. Let's take a look at this one. Right? So we want to integrate from -6 to 2, the integral of h of x dx. We want to evaluate that. Well, I don't see an integral from -6 to -2. I see -2 to -6. We know that this is the same as the opposite of the integral from -2 to -6. Right? So I can do, when I make it the opposite, I have to switch it. Right? So if I want to switch these so that the smaller number is at the bottom and the larger number is on top, I just have to take the opposite. Right? So you can switch the limits, just switch the sign. So now our answer is not going to be -4, it's going to be the opposite of -4, or +4. All right, so now we want the integral from -6 to 3. Well, we've already switched it once from -6 to 2. That gets us part of the way. Now, can any of our functions pick up from -2 to where we want to end up, which is +3? Well, yes, right? This one starts here at -2 and ends at 3, right? So we could use that one. So notice this one is starting where the first one left off. All right, so we would add the opposite of -4. And then +6. So that would give us 10. Okay. So you should be able to rewrite these as with the different integrals you would use to equal the same thing. And then you can substitute with the values. All right, so now we want to go from -6 to 5. Well, this one actually was a pretty easy one. So from -6 to -2 would be the opposite of our -2 to -6. And from -2 to 3, we would pick up with this one. And then finally, from 3 to 5, we have this one. So notice each one is, the next one begins where the previous one leaves off. And so now we can just combine these answers. So we have the opposite of -4 plus 6 plus 7, and that's going to give us 17 as our answer. Right? So that's the last one we're going to look at today. In class, we're going to look at an introduction to substitution because we need some more tools in your toolbox for integrating because there's a whole lot of functions that we won't be able to integrate without some more tools. And then we'll combine that with the definite integral. Right? So we'll look at substitution and using that as a way to integrate, and then we'll be combining that with our definite integral. I have one more problem for you. This was a closing that we did not get to today in class, and I thought it was perfect after the podcast. Now, if you've already turned in your closing for the week, no need to worry. You can just write this on a piece of paper and I'll just add this to your score. But this is the last of the closings. I was trying to get that to look straight. I guess it's not going to. And when I ask you to find the area under the curve, you can use any method you want. Right? So it's not a geometric shape, so actually don't use that one. You could use a limit of Riemann sums, or you can just integrate this one numerically and evaluate and give me your answer. So whichever one you like is fine with me. All right, so this is the last problem I wanted to show you, and I'll post this problem as well, but you could just pause the tape and answer my question. All right, so thanks for watching. Bye for now.